All right, welcome one, welcome all. How are you guys today? I'm glad to hear it. I hope you guys are well. I hope this does nothing to change that. It is Tuesday, our second happiest day of the week. The words are actually in frame, so we've got that going for us. All right, so I think we have 5 problems here. I think we can get through them in relatively short order. So our first question, we have a pipe full of air. It's open on one side and closed on the other. We will invert it such that the open side points down and then plunge it into the water, fresh water. So we don't have to worry about, not knowing densities and such. And we're going to plunge it into the water until the water level inside the pipe achieves a level of half L. So the pipe's actually 25 meters long, so I think that makes it 12.5 meters is L over 2. We want to know what is the height or the depth H of the bottom of the open side, the bottom side of the pipe, when this occurs. To make our lives easier, so we're not taxing our live studio audience too much, we're going to start with the assumption that the temperature is the same everywhere. So it is whatever it is up here, it's also everywhere throughout the water. Yay? Awesome. Okay. So what do we know then? Well, we can examine. So note, first of all, that there's water everywhere down here. There's water level. The water level inside the pipe is up to here. And there's air trapped above. And so we could rely on the ideal gas law here, right? We could say that PV over T is NR. And so the number of moles shouldn't change. R won't change. And so treating the air as an ideal gas, P naught V naught over T, or T naught, has to equal P later, V later, over T later, but T later is also going to be T naught. Does that kind of work? Or that P naught V naught equals PV. We have that V naught is just A times L. Do we see why the original volume is A times L?
Because it's a cylinder.
Because it's a cylinder, or even if it's not, right? The cross-sectional area A times the total length is full of air originally. So afterwards, that is B. Afterwards, we have some new pressure, P. And what is the new volume?
A times L over 2.
Excellent. A times L over 2. Nice thing that happens here is that A cancels, which is good because we didn't tell you what the cross-sectional, we just told you the length of this pipe, we didn't tell you the cross-sectional area. And so we can say that the new pressure, P, is going to have to be P naught, well, the L's go away, the A's go away, times 2. Yeah? So then we can apply Bernoulli's, right, our Bernoulli's equation thing isn't moving, and so I can just say that in order for this to not move, the pressure 2p naught plus rho times g times L over 2. Yeah? That's the pressure here from the column of air and the water above.
Wait, what is that equation supposed to represent?
Well, it's half of an equation. So this also needs to equal the pressure here, right? Otherwise, this particle would be driven here, or this particle would be driven here if they aren't at the same pressures. Yay or not yay? So let me write this smaller that it fits. 2p naught plus rho g L over 2 equals, well, p naught plus rho gh okay.
Sure.
If we do that and bring this there, I get p naught plus rho g L over 2 is equal to rho gh. And so h should be p naught over rho g plus L over 2.
Undo it.
Oh, and have we previously heard that it's dark in here?
I got 22.86.
22.86 meters.
Yeah,
Seems reasonable-ish.
was off by 0.5. Which doesn't make, wait, so what I thought was we need to find the height of the water where the pressure is equal to the pressure of the air if it's compressed into half of what it originally was.
So what we know is that I actually don't think that what you're saying is wrong. That should also be true. But what we know is...
No, I actually got the same answer as you. I didn't add the 0.5. I added 12 instead of 12.5, so I actually did get the same answer.
I was going to say, because that should give the same answer.
It would have been really
We're saying
weird
the
if it was
same
off
thing.
by exactly 0.5.
Okay, then we're happy.
Well,
We're not happy.
What we're doing is the same thing, because
It is. We're just, it's which direction we're insisting on the same ultimate condition. We're just approaching it in two different ways.
So the pressure at, so there's some height. This water is at like some depth in this water,
Yeah.
and the water at that depth has to have the same pressure as the air right there, right? That's what I did, and I got the same answer.
That should also be true, yes.
Okay.
Yeah, because that's why the water has come to this point, right?
Because
the
the
water at
pressure
this
is
point has to
equal.
have the same pressures.
Okay, that one
All
I
right.
don't know what to do because there's no question.
Well, I had to give myself a running head start here. What was I doing in this? Ideal gas fills a volume VA held at a fixed temperature of 300 Kelvin with an initial pressure of 500,000 Pascal. It's connected via a small tube with a valve to another volume VB that is 4 times greater than VA that is going to be held at a fixed temperature of 400 Kelvin with an initial pressure of 100,000 Pascal. The question at long last
Right.
is when we open the valve, and a common pressure is achieved. What is it? And I want to stress that even after the valve is open, this regulator is going to hold this volume to 300 Kelvin and this volume to 400 Kelvin, and we're not going to consider any volume of gas actually living in that tube. So, questions, comments, concerns about any thoughts as to how to start? So, if we look at our initial state, right, we can write what do we know will be fixed from before the valve is open to after the valve is open? Temperature, what else?
A volume.
Total volume, you're right. What else?
Amount of moles.
Number of moles, right? So if I wanted to write the number of moles that we initially had in VA, how could I get there? So looking at our ideal gas.
Oh, as an equation of, when you do PV over TR.
Yep. So that's how many moles were originally in A. How many moles did we originally have in B?
Same thing, but for B instead of A.
So PB, can I say 4 times BA just to save ourselves a line of algebra?
Sure.
Thank you kindly. Yeah? And then, when all is said and done, we still have the same number of moles. So can you template this for the after case?
Well, it would just be, I can just write P.
Excellent. So, and then the other stuff remains fixed, right?
Oh, and then that's, oh, okay.
Yeah? And note that they all have a VA in them and an R. So I could divide through by VA over R. Okay? And so we have well, we can plug in numbers at this point. PA was 5 times 10 to the 5. Over 300 Kelvin plus 1 times 10 to the 5. Probably divide through by 10 to the 5, but oh well. Over 400 Kelvin needs to equal P times 1 over 300 Kelvin plus, oops, did I drop a 4 here? 4 over 400 Kelvin. Yay?
Yeah. I just divide both sides by.
And so I could write this as 1 over 100 or 3 over 300. Is that true? 4 over 400 I could also write as 1 over 100.
Yeah.
Which is the same as 3 over 300.
Yeah.
So I could add that directly to this and say that this is P times 1 over 300 Kelvin plus 3 over 300 Kelvin is P times 4 over 300 Kelvin. Is that 8 times 10 to the 5 over 300 over here?
I'm just plugging in my calculator. I don't know.
Three hundreds go away, 8 over 4 is 2. P equals 2 times 10 to the 5.
Yep.
Does that make sense?
Yeah.
Does that make sense to everyone else? Wonderful. Thank you for saving me from having to learn ventriloquism. It's easier with the mask. Yes, Mark, that makes perfect sense. All right. Moving on to stuff that we were talking about yesterday in lecture. If we have the effective temperature of interstellar space is about 2.73 Kelvin, as measured by the cosmic microwave background radiation, CMBR. Interstellar molecular hydrogen. Can we figure out what the root mean square speed is? Somewhat of a plug and chug type problem, but I think it'll set us up well. So we had the half, should be careful, half V RMS squared is equal to 3/2 kBT. So VRMS then should be 3 kBT over m under the radical. So three times 1.38 times 10 to the minus 23 joules per Kelvin times 2.73 Kelvin divided by 2 times 1.67 times 10 to the minus 27 kilograms.
183.95.
183?
Yep.
What are the units? What should they be?
Meters per second.
True. It's pretty darn fast, right? The RMS speed of molecular hydrogen, really, really darn fast. Put it in perspective, the speed of sound here on Earth, cool dry air, somewhere around 340 meters per second. So, it's more than half Mach 1, right? We're good on this?
Yeah, that makes sense.
So, at 44 degrees Celsius and at a pressure of 1.23 times 10 to the minus 2 atmosphere, the mass density of a given gas is 1.32 times 10 to the minus 5 grams per cubic centimeter. First question, what is VRMS? The second question, what is the molar mass of this gas? And unstated, or at least unwritten, can we figure out what the gas is, or likely to be?
Well, we can still do 3 kBT over m. Square root of 3 kBT over m. Wait, no, we don't have them. Oh, we don't have the mass of it.
So we did a variant of this question last week, which I know everyone saw the video of, where it looks like there's that extra piece of information you would like, but you didn't actually need it. And at least to first order, the same holds true here. So last week we tackled this with an ideal gas law, and rather than solving directly for V, we solved for N over V. We're going to take a similar approach this time. So we could say that, well, let's put these in units that I'm more comfortable with. They do this in NRT. They did. So 1.23 times 10 to the minus 2 times 1.013 times 10 to the 5 Pascal. There's our pressure. V I'm not so sure of. N I'm not so sure of. .314 joules per mole Kelvin. Temperature of 44 plus 273 Kelvin. And so now let's see if we can suss out N over V.
Let's see where this is going.
So let's see. So let's see.
Oh, you wanted me to put it on the calculator.
That's all right. You have. Let's see. 27, that leaves 17, so 317.
Is that what it said?
So I think this is 0.47. I don't know, I'm going to keep extra sig figs here just for the time being. That'll be moles per cubic meter. Yay? To make my life a little easier, how many cubic centimeters in a cubic meter?
Million.
A million, so I'm going to divide this by a million.
Now you're going to multiply it by a million.
I want to turn it into per cubic centimeters.
Oh,
So I think that this is 4.7275. 4.7275, yeah. Times 10 to the minus 7 moles per cubic centimeter. So I have moles per cubic centimeter. What else were we given in this?
density.
We're also given density in grams per cubic centimeter. And so if I want grams per mole instead of moles per cubic centimeter, how can I take what I've gotten?
You divide the density of the gas by the...
Yeah. So if I take rho over is that what I want to do?
Yeah.
Yeah. I'll get grams per cubic centimeter divided by 4.7275 times 10 to the minus 7 moles per cubic centimeter. I will wind up with shift 1 over x times 1.32 x negative. I'm getting 27.92. Grams per mole. Turning to our periodic table, what are likely culprits? Well, you'd see that N has a molar mass of 14, and so this a common culprit that has 28 grams per mole would be N2. So good suspect at least. Maybe carbon monoxide, is that also?
Oh yeah, that's about 14.
12 plus 16 could, so maybe carbon monoxide also? I don't know, you can play around with the periodic table until, see what else could get you to roughly 28. But things that you're likely to encounter in your ambient air, well, plenty of nitrogen, right? Maybe some carbon monoxide too. That is part B. So how can I tackle part A? Well, this is M, right? The molar mass. But that also means that little m is roughly going to be 28 or 27.92 times 1.67 times 10 to the minus 27 kilograms. And so we can turn to the problem that we just did to get VRMS. VRMS is 3 times 1.38 times 10 to the minus 23 joules per Kelvin times temperature of, we said that was 317 Kelvin over 28 times 1.67 times 10 to the minus 27 kilograms. So let's see. And did I not square root that? Wait, how is that bigger? 317. I'm getting about 530. That seemed in the ballpark. 529.8. So the root mean square speed of nitrogen at 44 degrees Celsius at a fairly low pressure, right, is about 530 meters per second. Fairly high. Let's try one more just to palate cleanser sorbet. So we talked about this in lecture yesterday. What were the major constituents of stuff in the air in this room? Gave me a host of things, but the major constituents of air would be nitrogen and oxygen. And so let's assume that those are the only two things. They're not, but let's pretend, because it makes this more tractable. Can we use this to figure out what the fraction of nitrogen is in this air? So I might set this up as the overall density of air is some fraction, I'll call it, I don't know, Fn2 of rho n2 plus, well, if these are the only two things that make up air, and again, they're not, what's the fraction that makes up oxygen? How about 1 minus Fn2? I guess I could have done this in steps. Doesn't take up that much space. FO2 times rho O2, but FO2 is going to be 1 minus Fn2. Yay? And so now we can plug in maybe multiply out just to make our lives a little happier. Did I drop? I think I have that right. So we can say that rho air minus rho O2 is equal to Fn2 times rho N2 minus rho O2. Or that Fn2 is rho air minus rho O2 over rho N2 minus rho O2. So plugging in values, 1.293 kilograms per cubic meter minus 1.429 kilograms per cubic meter over 1.250 kilograms per cubic meter minus 1.429 kilograms per cubic meter. And minus 0.136 over, I can do this in my head, but minus 0.179, so 0.136 divided by 0.179 is about 0.76, or the air in this room, if it were, if it were 0 degrees Celsius, 1 atmosphere, and it were just made of oxygen and nitrogen, would have about 76% nitrogen, about 24% oxygen. Questions, comments, concerns? We are up at about 4:30. I will pause the recording here. As always, you guys are awesome. Have wonderful days. Thank you for stopping by. Don't be strangers. Enjoy your days, but not so much that we don't see you next time.